Session 9, Neutron Network, Technical Deep Dive, on request, extra lecture. Agenda of the session is Introduction to Neutron, Neutron namespaces, deep dive, and conclusions. Openstack networking before Neutron. Before Neutron was introduced, NOVA offered networking as a service is OpenStack. That was with the name NOVA Network. Before Quantum, that was the project name of Neutron. NOVA Network is still present today and can be used instead of Neutron. Points to keep in mind is limited network topology supported if you are using NOVA Network, and only flat is supported. Tenant A, tenant B, tenant C, all are on the same flat network. Machines can connect to the same. Overlapping is not possible. Centralized admin router, and this is flat networking topologies. Flat DHCP, flat plus DHCP. You can see DHCP server is also configured here, and this is flat plus DHCP example. VLAN DHCP is also supported. VLAN DHCP. In this case, what we have is a centralized admin router, which we have a tenant network, and disconnected or different or independent isolated a tenant B and isolated a tenant C. This is virtual LAN, virtual local area network with DHCP. No three-tier networking topology is supported. Like we require that layer 3 or level 3 or three-tier topologies they were not supported. That is the three-tier network topology were not supported if you are using NOVA network. That is before Neutron. What was happening? In fact, NOVA offered networking as a service in OpenStack, that is NOVA network. It was only offered before Quantum, as I said. Limited network topology supported, limited scale and network services supported, and scaling L2, that is layer 2, using VLAN. DHCP and DNS using DNS mask. Security using IP tables and hypervisors. IP management using SQL DB table. Limited network services were there. No self-tenant L3, no load balancer, no VPN was supported. Nothing was there before Neutron. No interaction with third-party networking solutions. No ability to use third parties to overcome the limitations of NOVA network. Complex or limited high availability management and monitoring. That was definitely challenging. So why we need OpenStack with Neutron? Neutron improve NOVA network in multiple areas. Larger number of network topologies and services are supported, like load balancer, VPN, routers, virtual multiple routers are supported. We can have a tenant network, tenant B, tenant C. They can have independent isolated networks. So larger number of network topologies like L3 self-tenant provisioning, security, that is ingress and egress rules supported, load balancer as a service is supported, and VPN as a service is coming up and will be supported. Support overlay, remove the VLAN limitation using overlay with GRE. So like we have a hypervisor here, any L2, L3 fabric will work on this. So VM virtual machine 1 IP, virtual machine 2 IP, they can interact. So it removes that virtual LAN limitation, the flat IP network problem. So here hypervisor 1 IP can communicate with hypervisor 2, and GRE at VM virtual machine 1 IP can communicate with the virtual machine 2. So this is hypervisor 1 on your first compute node, this is hypervisor 2 on second compute node, and they can communicate, they can connect. Open solution. So VMware NX plugins, Linux based plugins, OBS plugins, Cisco US, that is the open solution. For third party solution means mapping to the physical network on the top of this. How it works actually. That was a brief idea, very brief list of features. We need to understand a few more concepts. And the answer to this neutron is coming from one word called namespace. The namespaces enables multiple instances of a routing table. Point to be noted, multiple instances of a routing table. One copy, another copy, another copy. So you can have multiple copies of the same routing table to coexist within the same Linux box. Because of this region, these namespaces make it possible to separate network domains. That means network interfaces, routing tables, and IP tables into completely separate and independent domains. So what is a namespace? Tenant 1 working on namespace 1, which will have its own network interfaces, routing tables, and IP tables. Tenant 2 will have its own independent namespace, its network interfaces, routing tables, and IP tables. And so on and so forth. We have tenant N with namespace N, network interfaces, routing tables, IP tables. So this gives you isolated network infrastructure for every project. In OpenStack latest edition, we call it as project. In earlier version, we used to use a tenant, and the same concept is used for Oracle Cloud tenant. So tenant is a valid technical term. Earlier it was in documentation, but nowadays you find project. I prefer the same thing. Below this we have Linux kernel global namespaces, which include network interfaces, routing tables, and IP tables, stack IP tables. And below that we have hardware. So this is the layered approach. We have hardware, we have physical infrastructure, Linux, and then we have isolated namespaces for every tenant, every project. So what are the advantages of this concept of namespaces? We can have overlapping IPs. A tenant can create overlapping IP addresses. That is a situation that gives freedom to cloud users because they are free to create any subnet of choice without fear of conflicting that of another tenant. Linux network namespace is required on the nodes running Neutron L3 agent, that is level 3 agent, or Neutron DHCP agent if overlapping IP is in use. The L3 agent, Neutron L3 agent is designed to use network namespaces to provide multiple independent virtual routers per node that do not interfere with each other or with the routing of compute node on which they are hosted, because they are hidden, they are in isolation, and you cannot directly issue IP command or IP address command or ping command to check the IP addresses on the node where this agent is configured. What if the namespaces are not supported? If the kernel does not support namespaces, then these limitations should be noted with Neutron. Neutron L3 agent is limited to providing a single virtual router per compute node. If namespaces are support, a single deployed Neutron L3 agent should be able to host multiple virtual routers. So this is one advantage. If namespaces are not supported, you can have only single virtual router per compute node. If namespaces are supported by the kernel, this is a kernel feature. If namespaces are supported by the kernel, then you can have multiple virtual routers. It is necessary to configure each Neutron L3 agent with universally unique ID, identifying the router instance that it hosts. This complicates the deployment, makes self-service provisioning of routers by tenant impractical. If namespaces is supported, the configuration with the UUID of the router it hosts is not required. If the host does not support namespaces, then the Neutron L3 agent and Neutron DHCP agent should be run on different hosts. They cannot be on the same host. This is due to the fact that there is no isolation between IP addresses created by L3 agent and by the DHCP agent. A downside of this is that by manipulating the routing table, the user can ensure that these networks have access to one another. Recognizing namespaces. How? Every L2 agent or private network has associated DHCP namespace. And every L3 agent or router has associated router namespace. Multiple network topology, network node, compute node, cloud controller node, all of them can have multiple network topologies. What all we run on network node, we run Neutron metadata agent, we run Neutron DHCP agent, we run Neutron L3 agent. This is what we configure on a network node. And we have plugins, L2 plugin or ML2 plugin, Neutron plugin agent, corresponding plugin. On compute, we have Nova compute service running and Neutron plugin agent running. On controller node, we have Neutron server, we have Nova API, we have Nova scheduler and Keystone running on the controller, and also we have Rabbit message queue service on the controller node and MySQL database. They are connected through management network. Network node to compute node are connected for data network, and then we can have API connection through the router API network on the cloud controller node, and then we can access the machines from internet through the router with API network framework on the through the controller node. So we connect to controller node, which is connected to network and compute node via management network and data network. External network are possible between network node and router directly, that is external network. So this is the multi-node network topology, how networking is configured between compute network and controller node. The namespaces, the same concept. When you create a router, you will find entry something like Q router, some encrypted code. Similarly, if you configure DHCP agent, you will find Q DHCP, some encrypted code. So router, and these are namespaces. You get into the namespace to access the details of the DHCP server or the router service. So you cannot execute IP command or ping command on these routers or DHCP namespaces, because this is a concept of namespace. That means you, in order to access the details inside it, you have to get inside them using a specific command. Let's understand this. We have a data center network. We have router namespace. A router is created. We have a private network, and we have DHCP namespace. These namespaces are not accessible directly. If you want to work inside them, you have to issue a specific command. Something like this. On network node, your IP namespace will be something like this: QDHCP, some encrypted name, and DNS mask is running inside it, and you have this interfaces in this namespace. Point to be noted, you cannot see these details with IP command. I will talk about these commands in a short while from now. And then we have bridge connected to this, and then Ethernet, that is external network. Similarly, on compute node, we have instance, we have tape drive, and we have bridge, and the connection details ETH2. Let's understand these plugins also, ML2, Layer 2, and L3 plugins. The modular Layer 2 or ML2 plugin is a framework allowing OpenStack networking to simultaneously utilize the variety of Layer 2 networking technologies found in complex real-world data centers. It currently works with existing Open vSwitch, Linux Bridge, and Hyper-V L2 agents. This framework is also intended to greatly simplify adding support for new L2 networking technologies, requiring much less initial and ongoing effort than would be required to add a new monolithic core plugin. There are a lot of drivers for ML2. Driver within ML2 implement separately extensible set of network types. Means it depends what driver is installed on your cloud, only then you will be able to create the specific type of virtual network. Multiple mechanisms can be used simultaneously to access different ports of the same virtual network. Mechanisms can utilize L2 agents via RPC or use mechanism drivers to interact with external devices or controllers. Type and mechanism drivers are loaded as Python entry points using the Steve-Door library. Then we have a type drivers for ML2. Each available network type is managed by ML2 type driver. Type drivers maintain any needed specific network state and perform provider network validation and tenant network allocation. The ML2 plugin currently include drivers for local, flat, VLAN, GRE, and VXLAN network types, which you might have configured when you configured Neutron. Then we have mechanism drivers. Each network mechanism is managed by an ML2 mechanism driver. The mechanism driver is responsible for taking the information established by the type drivers and ensuring that it is properly applied given the specific networking mechanisms that have been enabled. L2 agent, its main responsibility is to wire new devices, that is the tape interfaces created by NOAA, and to configure the software bridge on the compute nodes. There are usually two bridges, BRINT and BRTUN, that is this integration bridge and tunneling bridge. The INT is integration bridge. It's the bridge that takes care of tagging and untagging of traffic which coming in or out of virtual machines. To tag the traffic, it uses local VLAN ID and assign it to the network. This tunneling bridge, it takes care of translating the tagged traffic. It translates the VLAN ID into segmentation and using it then for tunneling. For example, You use GRE tunnels, the segmentation ID is used to specify the tunnel ID. The L2 agent is also responsible for applying security group rules, that is firewall rules, which implemented in Neutron by using IP tables and IP sets. This constantly communicate with Neutron server using remote procedure calls. Then L3 agent. While L3 agents share a lot of same architectural aspect as L2 agent, it is completely different. L2 agent getting you attached to your network. L3 agent get you routes attached to each other. That is interesting point. Major difference. L2 agent get you attached to the network. L3 agent get your router attached to each other. It moving data from one network to another, from your network to external world. Finding the router in IP or ipconfig. The Neutron L3 agent uses Linux IP stack and IP tables to perform L3 forwarding and NAT. In order to support multiple routers with potentially overlapping IP addresses, Neutron L3 agent default to using Linux network namespaces, as I explained, to provide isolated forwarding contexts. As a result, the IP addresses of the routers will not be visible simply by running this IP address list or ipconfig command on the node. Similarly, you will not be able to directly ping the fixed IP addresses. To do either of these things, you must run the command within the particular router's network namespace. The namespace have this kind of name like Q router followed by UUID of the router. This is the example, same figure I am referring here, DHCP router namespace and router namespace. So the L3 agent workflow. L3 agent listens for notifications. When anything changes on the router, Neutron server send notification to L3 agent. The L3 agent takes the notification it received and push it into processing queue because it may have more work than it handle at a given time. Normally, it pops right up to the top of processing queue and pulled out for processing. The agent has a capacity of networking on few routers at a time. If it is working on every router at the same time, things may get a little slower. There are two types of events that can be put in the processing queue. Changes in the router, usually caused by user action that changes something in the router configuration. L3 agent restart or exception thrown in such cases. It does a full resync. And then we have L3 agent also sends status updates in case ports or floating IP changes. Router internals. A network namespace is like a container or VM for network device. It's all about the network stack virtualization. Just like Nova relies on L2 agent to plug the port and do all the L2 wiring, L3 relies on L2 agent for that. Once those ports exist, whether it is OVS port or WETH pair, that is virtual cable, they can be moved into namespaces just like taking a wire and plug it into your device. Then L3 agent configure the IP addresses on the interfaces. It configures the routing, whether it is basic routing table or extra routes that have been configured on the router. It uses IP tables to implement the floating IP functionality, so it allocates a floating IP you associated with an instance. Neutron figures out which router that instance needs to go through to get the external network, and it uses NAT to implement that floating IP. On the router, there's a metadata access, shared access for instance without floating IP, and some of the advanced services also integrated into it, like VPN as a service and firewall as a service. Troubleshooting steps. First, you need to identify the correct namespace. Simply pgrep f1 DNS mask. First check whether DNS mask is running or not, and then select ipnetn command. This will give you qrouter and qdhcp. These are the namespaces. So perform general troubleshooting around the identified namespace. Have spin off an instance and it has IP address from horizon but cannot SSH, probably because interface has not assigned IP. So it can only view from VNC. So first you check whether DNS mask is running or not. If required, start it. Verify the IP address in the namespace if the DNS mask is running. So ipnetns. Then identify the DHCP network namespace, and this is how you use it. ipnetns, execute the QDHCP namespace, and then you use IP space A command inside that. Look at this. ipnetns, execute QDHCP namespace, and inside that you are using IP space A command, and you are getting all the IP addresses inside the DHCP which has been used. To verify what the expected IP address is, you can use OpenStack port list and OpenStack port show. When you use OpenStack port list, you will see the IP addresses, what all IP addresses have been assigned with their subnet IDs. And then you can use port show and specific show, and then you will see the complete DHCP details, driver IP, fixed IPs, what you are getting. So you will get comprehensive details. Then determine the leases. You can go to this file var lib neutron DHCP and network UUID, like here cat var lib neutron DHCP and the UUID. Inside that UUID you will find the file host. Check that file and that will give you the host and the IP address. If the DNS mask configuration is correct but the DNS mask is not responding with leases, the bridge interface is created, then kill using pkill command and then restart DHCP agent. If DNS mask does not include the correct leases, verify that Neutron server is running correctly and that it can communicate with the DHCP agent. If it is running correctly and the bridge interface is created and running, restart Neutron DHCP agent. These are some of the troubleshooting tips for Neutron related or IP address related problems. On the network node, DHCP agent is configured to use OVS or DNS mask. You can use grep command, etc neutron DHCP agent. Check DHCP. Similarly, grep DHCP. You'll execute DHCP if config command inside that, and that will give you the IP addresses only. Note that DNS mask log on to var log syslog in Ubuntu installation, and this is an example output from our system which I've been using. On compute node, you can use IP link, bridgectl show, and IP table save, TCP dump. These are some of the commands you can use on the compute node also for troubleshooting. On controller node, OpenStack NUT show, OpenStack subnet show, server create. This is creating server. We cannot do it right now because we have to first complete Cinder block storage. Only then we'll be able to create the instance. When a router or network is created, the namespace don't get created immediately. For network, the DHCP namespace gets created only when a VM is attached for the router, and namespace is created when a gateway is set. This means that an activity must take place before namespace get created. When a router or network is deleted, associated namespaces are not deleted. They need to be manually deleted. That's all for this session. Thank you very much.